Hey there, you again. I have my cup of tea to keep me warm as the cold weather creeps up on us. Anyway, how are you doing? Are you feeling burnt out on the semester? Well, I've personally felt burnt out on the semester by like week 2. So if you've made it this far and only now starting to get tired, then I think you're more than capable of getting to the end. But either way, think of it as like a workout. So, if you're working out, your brain is telling you that you're too tired to go on before your body is actually too tired to keep going. So I'm sure there's a metaphor in there somewhere. All right, so let's begin with a partial order. So a partial order is different than an equivalence relation. A partial order instead is a relation that is reflexive, antisymmetric, and transitive. So we have a few sets, and we want to determine whether these sets as relations are partial orders or not. We have the first one. Now we're given a set. Our set is 0, 1, 2, 3. Given that set, is A partial ordering? Well, no. We can give a counterexample. It's missing 1, 1. So no, A is not reflexive and therefore not a partial ordering. Okay, part B now. Is part B reflexive? And it is. Is it antisymmetric? Well, to show it's antisymmetric, we need to show there are no cases of symmetry. We can do this by testing every pair in which we'll call the left side of the pair A and the right side of the pair B, in which A and B are not equal. So right here we have 2, 0. A is 2, B is 0. A does not equal 0, so let's use that pair to test for antisymmetry. We reverse it. We have 0, 2. Is 0, 2 in the relationship? No. All right, that checks out. We have 2, 0, or 2, 3. Is 2, 3 reversed in the relationship? In other words, is 3, 2 in the relationship? No as well. And that's all we can check. It passes in both cases, so it is antisymmetric. Finally, we must test for transitivity. There are a few pairings we could test here. We'll do 1 or 2. We have 2, 3, and we have 3, 3. We see that the right side of the first pair matches up with the left side of the second. So that means 2, 3 should exist as a pairing. Does 2, 3 exist in the relationship? And it does. It's right there. So it is in the relationship. Transitivity holds in that case. We also have 2, 0 and 0, 0, right? Which means that, so this 0 might pair up with this 0 there. This 2 pairs up with that 0. So we should also have the pairing 2, 0. Is it in the relationship? And it is. So it is reflexive, antisymmetric, transitive, therefore B is a partial ordering. Finally, C. We have the following relation with a bunch of pairs. Is this a partial ordering? Well, we have 3, 1 in our relationship. We have 1, 2 also in our relationship. We have that this 1 pairs up with that 1, so that means we should have 3, 2 also in our relationship if it's transitive. But we don't. So it's not transitive, therefore not a partial ordering. All right, part D. Remember, it's a partial ordering, also known as a poset, if it's reflexive, antisymmetric, and transitive. Is it reflexive? Yes. Is it antisymmetric? We can test a bunch of values, but yes, it is. Is it transitive? And well, it wouldn't be. We have 1, 2. We have 2 comma 0, both in a relationship, but we don't have 1 comma 0. So no, it is not a poset because it's not transitive. Part E now is clearly reflexive, but it's not antisymmetric, right? We have 0 comma 1 right there in our relationship, which means that 1 comma 0 should not exist if it's antisymmetric. However, 1 comma 0 exists right here. So because of that, it's not anti-symmetric and therefore not a poset. Okay, so we have the following relationships where A and B are the set of all people. We must determine if they're a poset or not. So this first one, let's test for anti-symmetry. A is no shorter than B. Let's plug in 2 people. Let's say that Bob is no shorter than Jill, and this is true, it's in a relationship. Does the reverse hold? If this is true, then is this also true? Is Jill no shorter than Bob? Well, this also holds true. This is also in our relationship, because for Bob to be no shorter than Jill, then it must be that Jill is no shorter than Bob. Therefore, not a poset. This one's much easier than the first one. Is it reflexive? Right? Again, let's plug in 2 people. We don't even need to do that. Does it make sense to say that A weighs more than A? No. So it's not reflexive because A comma A is not in the relationship. A equals B, or A is a descendant of B. Well, this one clearly fulfills the property of reflexivity because A can equal B. It clearly fulfills the antisymmetric property because A is a descendant of B, and that means that B cannot be a descendant of A, so it is antisymmetric. And it also fulfills the property of transitivity because if A is a descendant of B and B is a descendant of C, then that must mean that A is a descendant of C. So it fulfills all 3, and therefore, yes, it is a poset. Finally, A and B do not have a common friend. It's not reflexive because A and A do not have a common friend. It makes no sense. A and A is not in the relationship, so it's not reflexive and therefore not a poset. You do know sometimes I make mistakes, but I'd like you to know that I only make those mistakes to get you guys to question the self-evident, right? You know, I wouldn't make those mistakes on accident or anything like that. I'm just getting you guys to pay attention, keep you on your toes. That's definitely the reason. All right, 9.6.8. See, when given this matrix, is it a poset? And we have the set A, B, C, D, so we know that we could represent our matrix with A, B, C, and D on the sides so that we know it's a poset, again, if it's reflexive, which it is. It also must be antisymmetric, so every 1 must correspond to a 0. All right, so all the 1s correspond to 0s on the mirror of the diagonal within our matrix. Finally, is it transitive? We have A comma C, so down A across C, which is in the relationship. We also have C comma D, which is down C across D, which is also a 1 within the relationship. So we should have A comma D. Is this within the relationship? Well, let's go down A across D, and we see that we have a 0 here. So at the intersection, we have a 0. So no, it is not within a relationship. It is not transitive. So therefore, this relation represented by this matrix is not a partial order. Okay, so draw a Hess diagram on divisibility. Okay, so we have a set here, and we also want to determine what the hash diagram is with the relationship of divisibility. So you might also see it in S, R format. So sometimes you'll have the set, that's the set S, with the relationship replying to that set. So in this case it would be divisibility, so a divisibility symbol, but as you know, being the R, so S, R. But in this case, it's not in that format, it's just a set, and we're told within the problem that the relationship is divisibility. So to do this, we begin with the very left of our set. We have a 2, so 2 is going to appear in our hash diagram, our graph. Okay, so because there's no other nodes, we simply write the 2 on the first level of the hash diagram. Next, we have a 3. Does 2 divide 3? No. So 3 does not have a relationship with 2. 3 is going to go at the very bottom of our hash diagram next to 2, but not connecting 2, because they lack a relationship. Okay, we have 5. Does 2 divide 5? No. Does 3 divide 5? Also no. So 5 is going to go at the very bottom of our hash diagram. It does not have a relationship with either of the 2 previous nodes. Next, 10. Does 2 divide 10? Does 5 divide 10? So, because something divides 10, we're going to put 10 on the second level of our hash diagram and draw an edge from 2 to 10, and also 5 to 10. 3 does not divide 10, so we don't draw an edge from 3 to 10. All right, next, 11. Again, nothing divides 11, so 11 is going to be at the very bottom of our hash diagram, not connecting any other node. We have 15. Does 10 divide 15? No, so we're not going to put 15 on the top layer, or on a new higher layer of our hash diagram. Does 2 divide 15? Only 3 and 5 divide 15, so 15 is going to go here, next to 10, but not connecting 10. And edges are going to correspond from 3 to 15 and 5 to 15. Finally, we have 25. 10 and 15 don't divide 25, so 25 is not going to go on a level higher than either of those 2 nodes. 2 does not divide 25. Only 5 divides 25. And there, we're done with our hash diagram. We're done because we have placed all of our values within the set as nodes in our hash diagram, and we've drawn all the relationships possible to represent a partial ordering. Okay, we're given a poset, this set, and this relationship, and we want to determine or answer these questions. And to do that, we're going to have to draw a hash diagram. So again, it's on divisibility. So let's begin with our hash diagram by starting from the left side of our set. We have 2. 2 is alone, so we draw 2 as a node. We have 4. 2 divides 4, so we put 4 into our hash diagram and connect it to 2. We have 6. Only 2 divides 6, so we put it on a higher level and connect it to 2. 9. 9 is alone. We have 12. 12 divides 6 and 4. Or I'm sorry, 12 is divisible by 6 and 4. So we draw edges from 6 and 4 to 12. We do not draw an edge from 12 to 2 because a relationship already exists in our hash diagram. 2 divides 4 and 4 divides 12. Therefore, 12 also divides 2, or is divisible by 2. So there's a relationship from 12 to 2 that exists through 4 and through 6. So we don't need to draw an edge in this hash diagram. Okay, 18. 18 could be over here. 18 is divisible by 6, 2, and finally also 9. After 18 we have 27. 27 is only divisible by 9. We have 36. 36 is divisible by 9, 18, 12, 6, 4, and 2. We're only going to connect it to 18 and 12 because those are the highest, we'll call it a level, in our hash diagram. All right. After 36, we're given 48. 48 is divisible by 12, first and foremost, then 6, 4, and 2, consequentially. We have 60, again, that's only divisible by 12 on the highest level of our hash diagram. And finally, 72. 72 is divisible by 36, so we connect it to 36. And again, the relationship continues downwards. So 72 is divisible by 36, which is divisible by 18, 12, and then those are divisible by 6 and 2. And you can keep going that way to determine whether what's divisible by what. But this will be our hash diagram. Then we answer. Part A, what are the maximal elements? Well, the maximal elements are simply those that don't have any relationship on top of them. So that would be 27 because there's no relationship above it any further than itself. 72 because it's an endpoint. There are no relationships on top of 72. 48 and 60. Okay, that answers that question. What are the minimal elements? Well, these are elements that don't have any relationships below them. That would only be 9 and 2 on the very first level of our hash diagram. Okay, what is the greatest element? The greatest element would be the element that everything goes to near the top of our hash diagram. But no greatest element exists because we have 4 potential greatest elements, 60, 48, 72, and 27. So we do not have a greatest element because we don't have a single element that everything points to near the top. So no, there is no greatest element. Is there a least element? Same thing. We have 2 possible least elements, so we don't have a least element. If there was another node below 9 and 2, another element, then we would say this is the least element. But it does not exist. Nothing funnels down into a single node, so we do not say there is any least element. No. What are the upper bounds of 2, 9? Well, this is 2, and this is 9. The upper bounds are simply values on top that they share. So 9 connects 18, and 18 connects 2 through 6. So 18 is one possible upper bound of 9, 2. Another one would be 36, because 9 divides 18, which divides 36. 2 divides 4, divides 12, divides 36. So 36 is another. We would not say that 12 is an upper bound of 2, 9, because to get to 12 through 9, we have to go up, down, and then up again. So we do not say that 12 is an upper bound of 9. So therefore, it can't be an upper bound of 2, 9. Okay, other than 36, what else is there? Well, 72. 72 can be divisible by 9 and also divisible by 2. So finally, 72. And those are the 3 upper bounds of 2, 9. This is the correct question. F. What is the least upper bound of 2, 9? Well, that's easy. It's just the least element of what we've already found. 18 would be the least element of 18, 36, and 72. So we would say that 18 is the least upper bound. What are the lower bounds of 60, 72? Well, here's 60 and here's 72. It's the same thing but in reverse. We go down from 72 and down from 36 to get to 12. Starting at 60, we go down once to get to 12. So therefore, 12 is one lower bound of 60, 72. 18 would not be a lower bound because although we go down and down again to get from 72 to 18, we have to go down from 60, up from 12, and down from 36 to get to 18 from 60. So because you don't just go down on both to get to the same element, we would not say that 18 is a lower bound of 60, 72. Instead, 12, 6, 4, and 2 are lower bounds of both of those elements, right? Because 4 is divisible by, or 4 divides 60, and 4 also divides 72. 6 divides 60, and 6 also divides 72. Finally, 2 divides both of the elements as well. So those are our 4 lower bounds of 60, 72. Finally, part H. What is the greatest lower bound of 60, 72? Well, that's just the greatest of these elements, which would be 12. It's the first one that we find on our hash diagram going down for both elements. So 12 is our greatest lower bound. And then we're done. So we're asked to find a compatible total order for this poset given this following hash diagram. So here's our hash diagram. To find a compatible total order, we just arbitrarily, and arbitrarily just means randomly remove one of the lower bounds and then kind of put it onto our scheme. So we have 3 lower bounds, A, B, and C. Let's just remove one of them. Let's remove A first. So then A is removed and we begin with A on our scheme. Then we put the following symbol, kind of just like a little symbol that represents that A is the first one we chose, and the next one's going to be the next one we choose. So then now there are 2 possible choices of lower bounds, B and C. D is not a lower bound because B is below D, so we wouldn't choose D at all. Let's choose instead B. So we cut B away and cut the edges that correspond to the next, that were attached to B. All right. From B, we can either choose D, E, or C. Let's get rid of C and add it to our scheme. All right, now we have 3 options, D, E, or F. Let's cut away D. Okay, so from there we have 3 options again, I, E, or F. Let's get rid of E. From E, we'll get rid of F. After F, let's get rid of G. After G, let's choose H. After H, we can choose I. After I, we can choose J or K. Let's choose J. Can you see that? So after J, we must choose K because K is the only lower bound in the remaining diagram. So we remove K. Then we can randomly remove one of the last 2 nodes because they would both be lower bounds of our given graph. So let's choose L and then N. And then this would be our final scheme, and this would represent a compatible total order with the poset that we were given as a diagram. Okay, so write an algorithm that takes as input a list of n integers and produces as output the largest difference obtained by subtracting an integer in the list from the one following it. Okay, so this is just like coding, but we're not allowed to use a language. In other words, our algorithm must be language agnostic or pseudocode. To begin, let's just write a function. Let's say instead of putting function like we would in something like C, for example, let's put procedure. Call it a name. Let's call it the large difference for largest difference. And as input, we take a set of integers called A, for example. So the first one in our set will be A1, A2, dot, dot, dot. That means it goes all the way to AN. And these are integers. And this is just given in the problem. It says, as input, a list of n integers. We have n integers here, from 1 to n, and we call them a. All right. So, from there, let's create a variable called max, which will save the current maximum value within our algorithm. From there, let's make a for loop. In this for loop, we're going to iterate n minus 1 number of times, right? Because if we're on the last variable in our loop, then there's nothing to check after it. So for I equal to 1, 2, n minus 1, we do the following. Again, it's n minus 1 because if we get to n, we can't check n plus 1, right? That element would not exist. So we only get n minus 1, and then we can check n, and that would be the end of our for loop. If max is less than a of I plus 1, then do the following. Let's update our maximum value. Max is now equal to I plus 1 minus a of I. Finally, we return. Think of this as kind of like leaving a comment in the code. That way, the person reading our pseudocode knows that max represents the largest difference. Next problem. Devise an algorithm that determines whether a string of n characters is a palindrome. Okay, so I already set up our pseudocode kind of format. We have a procedure, which is just a function. We'll call it palindrome. We're given a through n integers, or characters, which represent a string. Let's create a variable called check. Check begins with true. At the very end, depending on what happens over here, check will return true or false. It'll return true if and only if the string we're given is a palindrome, and false otherwise. So, well, this is easy. Right, remember a palindrome is a string that reads the same forwards and backwards. For example, race car. I'm sure there's a million more examples you can think of, but we begin. So we take a for loop, we'll call it I, and it's equal to 1, and it goes all the way to the floor function of n over 2, right? We only want to go halfway through our palindrome. And if we have an odd number of characters in our palindrome, we want to stop right before the very middle integer. So, for example, again, we have race car. Race car has 7 integers, so this loop is gonna go from R, A to C, and then finish. If A of I does not equal A of n plus 1 minus I, then check equals false. So how does this work? Well, in the first loop of our for loop here, we check A of I. A of I is going to be equal to 1. Just FYI, we're starting at 1 and not 0 because usually in pseudocode, we don't really begin with 0. We begin with 1. You know, not the computer science way. I know, it's heresy. But we begin with 1 instead, just to make it code agnostic. Okay, so if A of I, which is R currently, does not equal to A of n plus 1, that would be this blank space right here, minus I, so it's minus 1, so we would get R right there, then check is equal to false. But R is equal to R, so this holds true. On the second loop, we would check A. A of I, which is just the second letter A, is it or is it not equal to A of n plus 1 minus I? That gives us this A in the very back, right before the R. This checks out, so check is never set to false. If this A was a second A was anything but an A, then this would be set to false, and then the loop would continue until it finished. It would never be able to set check back to true, and at the very end we would return check as true or false, depending whether or not we were given a palindrome as input. devise an algorithm that finds the first term of a sequence of positive integers that is less than the immediately preceding term of a sequence. So we have a procedure, I've already begun it, we'll just call it find, and we're given a series of values which are positive integers. Okay, so first we're returning the location. So let's have a variable called LOC for location, and it's set to the 0th index because we don't have an index yet. We don't know the location. So let's set I, which is some variable we're going to iterate through, to 2. While I is less than or equal to n, remember we have n number of values as input, so that's where n is defined. So while I is less than or equal to n, and LOC is equal to 0, if A of I is less than A of I minus 1, so that's the less than the immediately preceding term. So as long as if A of I is less than A of I minus 1, then location is going to be updated to the position of I, or the value of I within our loop. Else, I is equal to I plus 1. Kind of a roundabout way of just doing a for loop, right? I mean, we're just, yeah, okay. Anyway, it's the same thing though. This is going to loop through, and then once everything is finished, we return the location. So we need to use the greedy algorithm to make change using quarters, dimes, and pennies, no nickels, which uses fewest coins. Okay, so basically what it means by a greedy algorithm is that we use a dirty and cheap method of just putting in the largest quarter or largest coin into how many cents we have left to give change for. And through this method, we may or may not find the optimal solution. I believe in this case, it will give us the optimal solution though. So we're given 87 cents. Of the 3, quarters, dimes, and pennies, what is the largest denomination we can put into 87? Right, we can put a quarter in. In fact, we can put 3 quarters in. So we take 87, subtract 25 times 3, and we get 13 left. We now need to give change for 13 cents. The largest of these 3 is a dime that we can put into 13. So minus 10 equals 3. Then we put 3 pennies in. Minus 3 times 1. To get exact change for 87, we needed 3 quarters, 1 dime, and 2 pennies, so it's 6 coins total. Part B. Well, for 49 cents, we can put 1 quarter in. So we put 1 quarter in, we get 24 cents left to give change for. Let's put in 2 dimes. We get 4 cents left. Then we put 4 pennies in to get exact change for 49 cents, 7 coins. So part C now. For part C, we're going to need to use 3 quarters to get to 24 cents, and then we put in again 2 dimes and 4 pennies to get exact change for 99. And that requires a hefty total of 9 coins using the greedy algorithm. Finally, 33 cents. We can put in 1 quarter. We have 8 left. Then we put 8 pennies in because we are not allowed to use nickels to get exact change for 33. This requires 9 coins as well. So therefore, A uses the least number of coins, only 6 coins.